this is 40 Days of Chemistry Part 10, and this time I'm going to look at the skills topic. Don't forget that there is a 9.1 topic, the fifth of our 5 topics in the HSC course, focusing on skills. And the first section of those skills is what we call H11, which is planning investigations. Now, you should know all these skills from your work in your experiments this year, and what I've done is just highlighted a few things, the things you might have to actually answer sort of questions on in the HSC exam. And the first of these things is understanding the difference between quantitative and qualitative. That's something you should know. The second of these is identifying orders of magnitude that are appropriate. Just to be aware, the orders of magnitude means like the factors of 10 involved. It means you need to know your gigas, your megas, your kilos, your millis, your micros, and your nanos, things down there. You need to be able to use correct units for data, and that's probably involved with using your calculations. Make sure your volumes are in litres when you're doing calculations, your masses in grams, and your energies are in joules when you're doing your calculations. Another little bugbear of mine is that when you're writing kilojoules, kilo is a lowercase k and joules is a capital J, so it's little k, big J. It's not the other way around. It's a very common mistake. It's very frustrating. Please don't do that. The next thing is identifying appropriate technologies and strategies for data collection. Technologies for data collection are things like data loggers and probes, and an appropriate strategy for data collection and organisation is just putting things into a table using a spreadsheet, for example. This next section here, you need to understand the difference between dependent and independent variables. You need to be able to define them. You need to be able to identify what variables are kept constant in an investigation, and also know what a control is in an investigation. Where we use controls, things like the soft drink equilibrium experiment, we use controls, and we use those controls to account for any errors that occurred in the experiment. You need to design investigations that are valid and reliable. So you need to be able to define validity and reliability. Remember that for validity, the key thing for validity is, did you control the variables? That's what validity is about. Did you have your independent variable, dependent variable, and were all other variables controlled? So if ever a question asks you about validity, you must talk about the variables being controlled. If it talks about reliability, reliability is repetition and consistent results. Did you repeat the experiment with consistent results? This next section I've highlighted in brown is design and trial procedures. In the HSC course, you do what's called open-ended investigations, and we do them throughout all our experiments, all 27 experiments. Some of them were set up as open-ended investigations where it was your job as a student to figure out how to do it. And one of these, just as an example, if you're asked about an OEI one you could talk about, is you're determining the concentration of our sodium hydroxide sample. You're given some Winchester flasks of sodium hydroxide, and it was your job to design a method to figure out the concentration of that sodium hydroxide. And all of you chose to do a titration. You chose and designed your own standard of sodium carbonate. Then you chose the equipment, the steps, the chemicals, the indicators. You chose your calculation techniques to, first of all, figure out the concentration of hydrochloric acid, and then use that to titrate the sodium hydroxides. That's an example of an OEI investigation you did in your coursework this year. Risk assessments are the next thing on this page. We've done a lot of risk assessments. You should know what risk assessments are all about. And lastly, the difference between destructive and non-destructive tests. We talked about a lot of that in our nuclear topic when we talked about using radioisotopes to detect things rather than doing destructive tests. The next part of the skills course is performing investigations and analysing results, which is called H12. The first of those skills is talking about recognising where modifications are needed in experiments and the effect of those adjustments. Just an example of that was the sulfate in fertilizer experiment. We made a plan method, we talked about the errors that would occur and the modifications, adjustments that were needed. The next 2 points are about minimising hazards, minimising waste, and disposing carefully of waste materials. Don't forget, for all our acids and our heavy metals, we often store them for proper disposal. If you've got to dispose of an acid, you should neutralise it first. But don't forget, in all our risk assessments, it's 3 things you've got to talk about. You've got to actually identify the dangers. So you might say acids are dangerous, and therefore, why are they dangerous? Acids are dangerous because they're corrosive, they can burn skin and eyes. So you go, what's the danger of the acid? It's dangerous because it's corrosive. And the last thing is how you prevent that danger. So acids are corrosive, they can burn skin and eyes, therefore wear goggles, gloves, and lab coats. So you've gone for those 3 steps in your risk assessment. The next step is talking about data collection technologies, including data loggers and sensors. We did that in our computer-assisted titration and our water testing. We used quite a few sensors there. Measuring, observing, and recording results in accessible and recognisable forms. That means being able to use proper data tables and spreadsheets in chemistry. Accessing information from a range of sources. You did that in all your research. You used a number of textbooks, a number of websites for your research. Extracting information from numerical data in graphs and tables. That's just using your numerical skills. Summarising information from a range of sources. Once you've found the data, you need to be able to summarise that from a range of sources. identifying practicing male and female Australian scientists, which is why we did both of them in our assessment task. Assess the accuracy of measurements and calculations. Accuracy is how close your measurement is to the actual value. When we talk about validity, we mean was the experiment done to test the hypothesis? An accurate measurement is the actual measurement we got is the right measurement of one particular data point, I suppose. Best illustrate trends and patterns by drawing graphs or even computer graphs. That's something we've done before. Assessing reliability of first-hand and secondary information. Reliability of first-hand information obviously is have we repeated the experiment. Reliability of secondary information is can we find that information in lots of reputable sources. Okay, if you can find the same information in lots of reputable sources, that means it's reliable information. And also comparing information in the mass media versus scientific journals. We did that when we studied lead. We looked at an article about lead safety from a scientific journal versus an article about lead safety from a mass media publication. The next part of the skills section is H13, communicating information, and the key skills I'm highlighting here are, first of all, appropriate methods to acknowledge sources of information. That's to be able to write a proper reference. We practiced that when we looked up some of the esters and their uses, and we wrote down proper references from internet and book sources. Using symbols and formulae to express relationships. That means can you use your mole equations and other equations in chemistry. Using picture representations, that's mainly be able to draw appropriate structural formulae, particularly of organic compounds or carbon-based compounds. Drawing appropriate graphs, things like can you draw a calibration curve, and identifying situations where curves of best fit are appropriate. Now for AAS diagrams, most of the time you're going to get a straight line. There should be a perfectly straight line. But if you're ever given data to plot and it's clearly a curve, you can draw a curve of best fit rather than a line of best fit if that's the best thing to fit to your data. The last of the skills sections is H14, which is problem solving and scientific thinking. There's a few skills I wanted to highlight here. First of all, justify inferences and conclusions. You need to know the difference between an inference and a conclusion. An inference is basically an estimation of what you think has happened based on your observations. It's not a hypothesis. It's if you walk into a room and your dog's sitting there and there's like muddy footprints on the floor, you can probably infer that the dog left the muddy footprints there based on your observations. A conclusion, though, is drawn from more than one observation. It's your general perception of what's happened based on a whole lot of experimental data, like at the end of an experiment. Explain how data supports or refutes a hypothesis or a prediction. So you need to be able to look at data and say whether it supports or refutes a hypothesis. Making and justifying generalizations. That's where you make a broad general statement about chemicals or properties based on a few experiments. An example of that I want you to think about is the alkene versus alkane experiment. We only tested one alkene and one alkane. We tested cyclohexene versus cyclohexane, and we showed that the cyclohexene was more reactive than cyclohexane. And from that one experiment, we drew a broad conclusion that alkenes were more reactive than alkanes. And we could do that because we did a controlled experiment. The only difference between those two molecules was the presence of the double bond. Therefore, we can make the broad generalization that if you've got a double bond, you're going to be more reactive. Therefore, alkenes are more reactive than alkanes. Using models, including mathematical models, we use a lot of structural models and diagram models. We made multi-mod models, but also mathematical models. Things like our equations and our formulae are also types of models in chemistry. Using cause and effect relationships to explain phenomena. We did that in a whole lot of our controlled experiments. This is one example. We know that decreased pH equals increased corrosion rates. So you need to be able to say that the cause is the decreased pH and the effect is the increased corrosion rates, and obviously you should be able to justify why that is. The next thing is interconnectedness of ideas and scientific principles. There's a few times in the chemistry course where you've got to bring in a whole lot of different chemical principles together to explain something, and one example of that is buffers. For buffers, you've got to talk about Bronsted-Lowry theory, pH, as well as the Chatelain's principles. There's a whole range of things in chemistry we've got to draw on a whole lot of knowledge together, and can you connect those bits of knowledge together? The next section, I've highlighted a few here, B, C, and D. It's basically describing and selecting from strategies to solve problems. That's basically when you're solving your numerical problems, can you choose the correct equations and correct steps to solve that problem? And the last thing I've highlighted down here is propose ideas that demonstrate coherence and logical progression and include correct use of scientific principles and ideas. That's often the last mark of the high mark questions in the HSC. It's basically, can you string together a whole lot of arguments together to make something logical? And there's a whole lot of different topics we've studied this year where we've done a lot of practice in putting together long responses that are logical. The Haber process, S's, which involve a lot of steps, AES, how it works, a whole lot of steps involved there. The rusting process, we've got our procedure of describing the rusting process, a logical procedure, deep ocean corrosion, and there's a whole lot more, the acid rain logic arguments, the biopolymers, the ethanol fuel assessment, all those big, long response answers.